Hi everyone. So what I'm going to be looking at here is explaining how to do question 2, which is on the problem set that follows worksheet number 4. So worksheet or supplementary worksheet number 4 has a problem set, and question number 2 out of that problem set. You do have a full solution for it, but I'm going to show you how I worked it out. So the first thing we want to do to balance this by the oxidation number method is to assign oxidation numbers to each thing. So or to each element. Oxygen here is always assigned -2 unless it's paired to something more electronegative than itself, such as fluorine, which is not the case. So each oxygen is -2. There are 3 of them, so this contributes -6. This polyatomic ion has an overall charge of -2, which means that the sum of the oxidation numbers you end up assigning have to add up to -2. So if oxygen contributes a total of -6, then to end up with -2, selenium has to have an oxidation state of +4. +4, -6, -2. So then we keep moving. Iodine already is negative. It's provided here, -1. Hydrogen is an ion here, +1. Selenium, it's an element on its own, so neutral. Iodine, diatomic element, neutral. They're not in a compound, so that's how I know that they're elements, and elements are neutral. If they're in a compound such as this one, that's when they would have something other than 0 potentially. So here's water. You assign -2 to oxygen. +1 is the oxidation state, typically, not always, but typically assigned to hydrogen. So it's +1. Oh, I should mention oxygen. I said it's typically -2. It also could be -1, but only in a peroxide, for instance. So if this had been H2O2, that's like the little grouping you learned last year, peroxide, which is a singly bonded oxygen with a -2 charge. So that -2 is divided amongst these 2 oxygens. Each is -1, as opposed to the entire oxygen atom carrying the -2. That's another variation that you might see for oxygen. Okay, so now we want to look on both sides to see who's experiencing a change in oxidation state. So it's selenium. Before I figure out how many electrons are being transferred, I want to, or being lost or gained, I want to make sure that this is balanced. When you pre-balance, you're not balancing all the elements, only the ones that are specifically involved in being oxidized or reduced. So in this case, selenium is going from +4 to 0. So it's getting closer to 0. It's positive becoming less positive. So that means it's gaining electrons. So this is your gain of electrons is reduction. So GER, gain of electrons reduction. Okay? And how many electrons would it be? Well, there's 1 selenium here, 1 selenium there, so that's fine. So we know that each selenium is gaining 4 electrons. So this is a gain of 4 electrons. Whoops. So now let's see who else is experiencing a change in state, oxidation state. It's not oxygen. Iodine here is -1, here it's 0. So it's the iodine that's experiencing a change in oxidation state. Oh, I'm suddenly having trouble with this board. Okay, so -1 to 0, but notice that the iodine is not balanced. So because it's the entity that's experiencing, in this case, an oxidation, we want to pre-balance that to make sure that it starts off balanced. So we need a 2 there. And so that's ready now, and we can determine the total number of electrons that have been lost by all of this iodine. I know that it's losing because this is a negative charge and it's going to 0, so it's becoming more positive. It's -1 going to 0. It's got to be losing electrons to become a more positive or a higher oxidation state. Okay, so how many electrons would it be? So iodine is -1 to 0. That's 1 electron per iodine. But there are 2 iodines in total. So the total number of electrons, 1 per iodine, and there are 2, would be 2 electrons lost. Not sure why this is being a bit finicky here, but I think it's going to work. Okay, so I don't know if you can see that, but when I write over here, the cursor's writing over there for some reason. Anyway, so 2 electrons. So now I need to, and this is Leo, I like to always check to see that I have a Leo in the GER. So Leo, the lion, says GER, loss of electrons oxidation, gain of electrons reduction. That's one way to remember it. Because if you have 2 reductions without an oxidation, vice versa, something's gone wrong. You always need at least 1 oxidation, 1 reduction for it to be a valid redox reaction. Okay, so the 4 electrons has to balance with these, the 4 electrons lost has to balance with the 2 electrons, 4 electrons gained has to balance with the 2 electrons lost. So this needs to be multiplied here by 2, which then I'm going to transfer that 2, that becomes the coefficient. So there's a 2 here, no problem. 2 times 2, you just multiply, is 4. And then that 2 gets transferred to the other side as well, here. And see, there's 4 iodine, still balanced. You don't need to multiply anything here. So the last remaining thing to do is to finish off by balancing the water by inspection. You should not need to touch any of these other coefficients because you've balanced all these substances already. You just have to touch the water and any hydrogen ion or hydroxide that you may have left remaining, acid or base, okay? So let's balance the water and then finish off with the H+. So on this side, I have 3 O's, so I can put a 3 here, and the oxygens are balanced. So there's 6 H's there, none here, none here. So this is what I need to change to balance the hydrogen, so I need a 6 there. And so I'm just going to check and confirm. Yep, that's the answer I provided, so we're good to go. So hopefully that helps.